In our previous lecture, we have seen how to calculate the capacitance of two conductor system. So let us take a generalized case when there are now more than two conductors. So let us say there are n conductors, conductor 1 of different arbitrary shapes, 2, conductor 3, and up to so on n conductors. So in that scenario, what will happen? Let us see. So as I have told that the relation between V and Q is linear. That is, if Q rises by a factor of k, then V also rises by a factor of k. So this relation is linear. So we can hope that this will also follow superposition. So we can write that the potential of conductor 1 can be written as some factor P11 charge on conductor 1, P12 charge on conductor 2, P13 charge on conductor 3, and so on up to the nth conductor. Similarly, for the nth conductor, or let us say ith conductor, I can write Pi1 Q1 Pi2 Q2 plus Pii Qi plus Pin Qn. So in matrix form, I can write it as V1 V2 up to Vn is equal to P11 P12 up to P1n Pn1 Pn2 Pnn into the charges on the conductors from 1 to n. So this matrix is called as coefficient of potential. We will see that for a physical system, this matrix is invertible, that is, its determinant is not equal to 0. So we can see that if this V is equal to PQ, then we can write Q is equal to inverse of P into V. So this inverse of P is now written as CV. So this is coefficient of capacitance matrix. And in expanded form, I can write that the charge on conductor 1 is given as a linear combination of C11 V1 C12 V2 up to C1n Vn. Similarly, for ith conductor, Ci1 V1 Ci2 V2 up to Cin Vn. So in this way, we can find the charge or the potential on the conductor if we know these factors. And these factors, as we have seen, are just depending on the geometry and the media. Now for simplicity, let us take a case for 3 conductors only. This is conductor 1, this is conductor 2, and this is conductor 3. And let us say this is reference ground. So there will be a capacitance between these two conductors. Let us call it as capital C12. There will be capacitance between these two, C23. There will be capacitance between these two, C13. Similarly, there will be capacitance to ground, C11, C22, C33. So these are the capacitances which we have just drawn to build some picture in our mind. Now we will try to expand those matrix form. So Q1 is C11 V1 C12 V2 C13 V3. Q2 is C21 V1 C22 V2 C23 V3, and Q3 is C31 V1 C32 V2 C33 V3. This is the equation which we have written in our previous slide. Now from circuit theory, we can also write that Q1 is equal to some capacitance C11 V1 plus capacitance C12 and the potential difference between 1 and 2 plus C13, the potential difference between 1 and 3. Similarly, Q2 can be written as C21, potential difference between 2 and 1, C22 V2, C C23 V23, and this third one can be written as C31 V31 plus C32 V32 plus C33 V3. So you should understand that these C12, C13 and C11 or these coefficients are different from these coefficients, because here we are having potential with respect to the reference, but here we are having potential with respect to another conductor. So this is the difference. So now we need to find a correlation, because in network theory we are habitual, or we usually see this equation. So we want to draw some kind of picture in our mind with some interlinking between these two equations, these two kind of equations, or two matrices or these coefficients. So now let us do some algebra. So this Q1 can be written as C11 V1. Now V12 can be written as V1 minus V2. Similarly, this C13 can be written as V1 minus V3. So you see that Q1 now can be written as C11 plus C12 plus C13 into V1 plus minus C12 V2 plus minus C13 V3. Now I can compare this equation with the given equation above. That is, I can compare this equation and this equation. So from comparison of these two, I can see that this small C11 coefficient, the self coefficient, is equal to C11, C12, C13, and this mutual coefficient or the coefficient of induction, which we usually call them, is actually equal to minus C12, and similarly C13 is equal to minus of C13. Now we will little further ahead, we will show that this C12 is actually equal to C21 also because of reciprocity. Similarly, the C13 is also equal to C31 and C23 is equal to C32. So you see that from this picture we can directly write this coefficient by adding those capacitances which are directly connected to conductor 1, and this mutual or the coefficient of induction is just equal to the mutual capacitance between them, but the sign is opposite. As you know that the capacitance is always a positive quantity, so you see that these mutual terms or the coefficient of induction, which we usually call them, are negative. We can justify this. How? So you see that Q1 is equal to C11 V1 plus C12 V2 plus C13 V3. So what is C12? It is Q1 over V2 when V1 is equal to V3 is equal to 0. What does it mean? It means that this is, let us say, conductor 1, this is conductor 2, and this is conductor 3. So I will ground this, I will ground this, I will give a potential here V2. Now because of this potential, some charge will be there, some Q2 charge will be there, and this charge will induce a negative charge on it, and this negative charge will be given by the ground. So you see that this Q1 will be actually negative, and we have already taken that this V2 is positive with respect to ground. So you see that this mutual coefficient is negative or smaller than 0, we can say. So hence we have proved that these mutual coefficients in the coefficient of capacitance matrix are negative. Now we need to prove that C12 is equal to C21, or we want to prove the reciprocity. Let us do through the concept of energy. How we can do it? Let us say we are just taking now two conductors only. This is conductor 1, this is conductor 2. For sake of simplicity, we will just take two conductors. So we will raise this conductor to potential 1 and raise this conductor to potential 2. Now what we can do, we can achieve this situation in a way. First, what I will do, I will ground this conductor 2 and I will raise this potential to V1. So you might already remember that the energies which will be stored or consumed in raising this conductor to potential V1 is given as half C11 V1 square, and since it is already at potential 0, so there is no energy or work done to do that. We can calculate it by directly using energy is half of Q dV, and in this case it is C11 V1 dV1, and we will raise this voltage from 0 to V1, so it will be half C11 V1 square. Now in the next step, what we will do, we will remove this ground and raise this voltage to V2. So now the total energy stored will be half C11 V1 square plus half C22 V2 square, plus now since this conductor will get some charge, so this source, to keep still it at V1, will need to feed some charge. Okay, so it is already at potential V1, and because of taking this at potential 2, we will need some charge, that will be C12 V2. So this will be the work done to reach this stage. Now we can reach this stage in another way. How? We can first keep this as ground, the conductor 1, and we can charge this conductor to potential V2. So in that case, work done will be half C22 V2 square. Now I will remove this ground and connect it to V1. So energy stored will be half C11 V1 square, and it will be C21 V2 V1. Now these two configurations are same. This configuration and the previous configuration are same. So it implies, since it is conservative in nature, the electrostatic field is conservative in nature, so we can see that for both scenario the total work done should be equal, that is half C11 V1 square plus half C22 V2 square plus C12 V1 V2 should be equal to half C11 V1 square plus half C22 V2 square plus C21 V2 V1. So from this we can see that C12 is equal to C21. So in this way we have proved that these mutual coefficients are symmetric. So this matrix, the C matrix, is symmetric, means these are equal, and we know that these diagonal elements are non-zero. So there is a mathematical property that a symmetric matrix with non-zero diagonal have positive eigenvalues, or it implies it has non-zero determinant. So it implies that this is invertible. So we have proved that these matrices are invertible for a physical scenario and are also symmetric in nature. So in this way we can utilize this concept to a scenario when there are more than two conductors. If you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.